Up till now we have discussed about the wave functions, that is the general wave function that should represent a wave should be of the form y of xt is equal to f of x minus vt. And as an example we have discussed the sinusoidal waves in detail. So sinusoidal wave function, that is sine of kx minus omega t, represents a wave function. Now what this wave function is the solution of, that is of which equation this wave function is a solution. So we have to derive that equation. To do this, let us consider a wave that is traveling along a straight string in the positive x direction. That straight string has not been shown, but we consider a very small element, infinitesimally small element of the string at any time t and any position x. So the length of that element along the x-axis is delta x. And as we have discussed that every string through which a wave passes should have some tension, and that tension at every point should be tangent to that string. So over here, this one is a portion of the string, very small element of the string, and the tension at this end is represented by this blue arrow denoted by T, while at this end the tension is represented by the arrow that is headed downward and is represented by the same T, because the tension throughout the string is the same. Throughout the tension is not the same. It should be the regions which are stretched more, there the tension is greater, and some of the regions, for example the crest and the trough, are in relaxed mode, so the tension at those points is not like the tension at the positions other than the crest and the troughs. So in order to proceed to derivation of the wave equation, we analyze this element. This element should also have a mass, and as well as the linear mass density of the string will be involved, but we have to keep in mind these 2 points. The point A and B are the ends, and this is the element of the string. At this end, the tension makes an angle theta A with the horizontal axis, while at this end the tension force makes an angle theta B with the horizontal axis. So the net force acting on this segment in the vertical direction is this. Now look at the situation. Because there is no motion along the horizontal direction, so the net force along the horizontal direction is 0, and the only force, that is the net force, will be only in the vertical direction. So if we analyze the situation carefully, that is, if we resolve this t and this t into rectangular components, so over here the the y component of this force, this tension, is in the downward direction, while of this is in the upward direction. So their difference will be the net force. So the net force is T sine theta B minus T sine theta A, and which is equal to T sine theta B minus sine theta A. For the small angles, as this is a very small length element, so the angle that are subtended with the horizontal axis are very small, and for small angles we can use the approximation that sine of theta is approximately equal to tangent of theta, this equation. So to express the net force, that is this force, we can use tangent theta instead of sine theta. So this force, the net force, is approximately equal to T into tangent theta B minus tangent theta A. However, the tangent of the angles at A and B are defined as the slopes of the string segments at these points, because we know that tangent theta is equal to delta y by delta x, or dy by dx, or curly y by curly x, that represents the slope of the line segment, so or any curve. So the slope of the curve is given by curly y over curly x. So we can write this equation number 2 in the form T into curly y over curly x at point B minus curly y over curly x at point A. And now if we apply the Newton's second law to this segment, we can write the equation, this one, in this form, because the Newton's second law says that the net force acting must be equal to mass times the acceleration. So mass of the element is m is equal to mu delta x, where delta x is the length of the element and mu is the linear mass density, that is the mass per unit length. So this is F is equal to MAY, it is Fy, the force in the y along the y-axis. This is actually the force acting on any particle of the string in the vertical direction. This is MAY, and for M we can replace mu delta x, and AY, the acceleration as we define is, this is curly square y over curly t square along the y-axis. So from this equation and this equation we can write that this thing is equal to this, and the right and left sides are the net force along the y-axis, so the right hand side should also be equal to the net force along the y-axis. We are comparing the right hand sides. Mu delta x into curly square y over curly t square is equal to t, where t, the capital T, is not the time period of the wave. Remember, it is tension in this case. This is equal to curly y over curly x at point B minus curly y over curly x at point A. So if we if we bring this t to the left side, so this comes to be mu over t curly square y over curly t square, and bring the delta x to the right side, so that is curly y over curly x at point B minus curly y over curly x at point A divided by delta x. This thing represents when if we apply the limit in case, that is the limit when delta x tends to 0. So this thing defines the derivative of this function with respect to x, that is mu into curly square y over curly t square is equal to curly square y over curly x square. Now look at this mu over t. As we know, the wave speed on a stretched string is equal to t divided by mu under the root. In the previous lecture we have denoted the tension by F, so that is v square is equal to F over mu. So this is the reciprocal of v square actually. So we can replace mu over t by 1 over v square like this. and curly square y over curly t square, and that equals to curly square y over curly x square. This is the general wave equation that we have derived for the case of the stretch strain. So it can be verified that the general wave function f of x minus vt is a solution of this equation. Try it. Thank you.